Welcome back to section 4.1. Today we're going to be talking about linear and angular speed. Now, before we start talking about linear speed, think about distance traveled. Distance equals the rate times the time. That's what we've seen from Algebra 1, probably even back from middle school. Distance traveled is the rate, that's speed, times the amount of time traveled. Now, we could rearrange that to get that the rate is the distance divided by the time. By dividing both sides by t, we can get the rate is the distance over the time. Now, that corresponds to what we're going to be talking about with linear speed. The linear speed, and that's like just a fancy V there, that's the arc length, the length, divided by the time. Now, our arc length is S, or S theta rate times the theta, the radius times theta, that central angle. It's that distance over the time. Remember, theta is in radians. So when we talk about finding the linear speed, we're looking at S over T. Theta times R divided by the time. Angular speed, that looks almost like a W. That's omega. And that's going to be the central angle, theta, over the time. Once again, that is going to be in radians. The central angle divided by the time. So for number 35, the second hand of a clock is 10.2 centimeters long. That's going to be our radius. We're going to find the linear speed. So linear speed, we know it equals the arc length S divided by the time. So it's going to be theta times R divided by the time. Now, we have to look to see some information as it passes around the clock face. Now, the central angle, theta, it's going all the way around the clock face. That's one revolution. That's going to be 2 pi radians. And our time for the second hand to go around the clock is 1 minute, or 60 seconds. We want it in seconds because we're looking for it in centimeters per second. So it's going to be theta R. So it's going to be 2 pi times the radius, which is 10.2, divided by 60. So we're going to put that in our calculator. So you're going to get about 1.068 centimeters per second as the linear speed of the second hand around a clock face. So there's a couple of things you had to think about as far as what does a clock look like. Number 36, a lawn roller with a radius of 10 inches. So there's our radius is 10 inches, and it makes 1.2 revolutions per second. 1.2 revolutions per second. So what we're going to do is we're going to find the angular speed. So to find that angular speed, omega is theta divided by t. 1.2 revolutions per second. Now, it's not going just one revolution. It's going 1.2 revolutions. So we have to find out what 1.2 revolutions is. That's going to be 1.2 times 2 pi. And the time it's going to be is in 1 second. So omega is going to be 2.4 pi revolutions per second. So 2.4 pi radians per second, which is about 7.54 radians per second. There's our angular speed. Now we want to find the speed. Well, theta over t, that's just omega times r. So our angular speed times the radius, that's going to be 2.4 pi times our radius, which is 10 inches. So that's going to be 24 pi inches per second, or about 75.4 inches per second. There's our our linear speed. 37. Differences in latitudes. Assuming the Earth is a sphere of a radius 6,378 kilometers, what is the difference in latitudes of Lynchburg, Virginia, and Myrtle Beach, South Carolina? Where Lynchburg is 400 kilometers due north of Myrtle Beach. So think about the Earth. So what's happening here is that the radius, 6,378 kilometers, and the distance is not a line, but it's along that curve. So that length, S, is 400 kilometers. Now we want to find out how far apart they were. We're going to find out what theta is. So keep in mind, S equals theta times r. The arc length is theta times the radius. Now we can rearrange this to solve for theta. We can divide both sides by r, and theta equals S, the arc length, divided by the radius. So theta is going to be 400 divided by 6,378. And then we're going to convert that, that's kilometers over kilometers, they're going to cancel, times 180 over pi. So theta equals, so 400 times 180, and then divide that by 6,378 divided by pi, about 3.59 degrees. They're about 3.59 degrees apart from each other. Angular speed. A car is moving at a rate of 65 miles per hour, and the diameter of the wheel is 2.5 feet. Now, keep in mind, miles and feet. We have to make sure our units are correct. Find the number of revolutions per minute that the wheels are rotating. Now, for part A, we want to find out how far they're rotating. That's our circumference. Circumference equals pi times the diameter. So it's going to be 2.5 pi is the circumference of the circle, and that's in feet. Now, what we want to do is find the number of revolutions that they're going in a minute. So what we have to do is we have to convert a little bit here. So we have here is 65 miles per hour. Miles for every 1 hour. And here's how I convert. I'm going to convert my time first. Now I know I want my hours to cancel out. Now 1 hour is 60 minutes, so I want 1 hour on top, 60 minutes on the bottom. The hours cancel. So now our units would be in miles per minute. Now I need to change that to feet per minute. So 1 mile is 5,280 feet. So I need my 5,280 feet on top and my 1 mile on the bottom. That way my miles cancel. Now my answer would be in feet per minute. Now each revolution is 2.5 feet. So what I'm going to do is I'm going to multiply this by 1 revolution is 2.5 pi feet. Now that way our feet cancel and our answer would be in revolutions per minute. So you want to multiply all the numerators, multiply all the denominators, and divide. So you're going to get about 728.3 revolutions for every 1 minute. That's the number of revolutions per minute that the wheels are traveling. Now we can find the angular speed. For part B, the angular speed omega equals theta divided by t. Now theta is our revolutions. We're going around the circle 728.3 times in every 1 minute. So our angular speed, we need to change this to radians per minute. So then we're going to multiply that. One circle is 2 pi radians for every 1 revolution. Revolutions cancel, so then we have our answer in radians per minute. So our angular speed, when you multiply, you're going to get about 4,576 radians per minute. Basically what we were doing there is just converting it from revolutions to radians. And that would be the angular speed of the tire. We'll be working on this more. I know it's going to be a little confusing at first. A Ferris wheel with a 50-foot radius, so the radius is 50 feet, 1.5 revolutions per minute. So we need to find the angular speed. Now, 1 revolution is 2 pi radians. We don't have 1 revolution per minute. We have 1.5 revolutions per minute. So when we're looking at our omega, it's theta divided by t. Now theta is going to be 1.5 times 2 pi to find out how many radians we're going. So it's going to be 1.5 times 2 pi divided by 1 minute. So it's going to be 3 pi radians per minute, which is about 9.42 radians per minute. That's the angular speed, omega. Now we want to find the linear speed. Now the linear speed is the arc length over t, and once again that's theta r over t. We can use the fact that theta over t is our angular speed, so that linear speed is going to be omega times r, the radius. Omega, we just found, it's 3 pi, times the radius, which is 50. And that's in every 1 minute. So we'll end up with 150 pi feet per minute. You could write your linear speed like that. And 150 pi, that's going to be about 471.24 feet per minute is your linear speed. It doesn't ask us to change anything, so we can leave it like that in feet per minute. If we wanted to change it to feet per second, 471.24 feet for every 1 minute. What we'd have to do is convert minutes to seconds. Now 1 minute goes on top, 60 seconds goes on the bottom. So we'd just be dividing by 60. And you'd get about 7.85 feet for every second would be the linear speed. So depending on how you wanted the units, you might have to convert. They didn't tell us to convert to feet per second, so we could leave it as 471.24. Okay, I will see you in the next video to talk about degrees, minutes, and seconds. Thank you.